Okay, welcome to the Operations Research course. My name is Dr. Bright Oponefum. So this lecture will continue with linear programming. We'll actually look at some conditions that we will face when we meet or we encounter some of the linear programming problems. Like for instance, we've been talking about the decision variables obeying the non-negativity rule. However, in some special cases, we may get or we may want to also obtain negative variables. So how do we interpret such results, or how do we treat such situations in the linear programming environment? So look at that. We'll also look at special cases of non-negativity. If non-negativity exists, how we should handle it. Like for instance, if they are unrestricted variable, so the variable is unrestricted, it's unbound, and so any value is okay with us. Also the variables are negative within a particular boundary. How do we handle that, right? Then we'll also look at some special cases or complications in terms of if there is a tie for the pivot column, which one do we go for? If there is a tie in the pivot row, which one do we go for? Or what we call degeneracy. Then also we'll look at if we have an unbound problem, how does the simplex method interpret that, or how do we see that in the simplex method that we've already considered? What if we have multiple optimal solution mix or multiple optimal solutions? How do the simplex method interpret it? Then finally, we'll look at if the problem becomes an infeasible problem. How do we handle that? So stay with me and let's move on with our lecture. So we mentioned that there are special cases where we can have negative variables. There are special cases where we can, our results will actually lead us to having negative variables. So usually when we have negative variables, right, in the linear programming problems, right, we see that they do not actually satisfy the non-negativity rule, right? So all the analysis that we've done so far, the examples that we've treated so far, right, they are based on having a non-negativity restriction, right? Restriction. So that is actually true in most practical situations, right? It's very true in most practical situations. However, in some cases, decision variables can be used to define such concepts as production rates or even speed of moving vehicles, where we have a rate moving can have a negative rate or a decreasing in rates, right? And also an increase in the rate. So we have speed, we have high speed, and we have low speed, right? So we could use negative values to imply decrease in the rate of production, right, of a particular system, or negative value to depict the rate of decrease in the speed, right? So if it's a production, then the rate of decrease in the production system, we can use negative values to imply that, and also positive values to imply an increase in the rate of production in the system, right? So this means that since negative values are not allowed in simplex method, right, any problem with possible negative value should be converted to an equivalent problem with positive variables. So then how do we handle that when we know that we are dealing with, so the decision variable actually concerns rate of production or rate of a moving vehicle, or rate of let's say momentum or movement of any object, right? So how do we handle it in a simplex form, right? So there are two general cases when non-negativity actually exists or they are preferred, right? So the first one is variables that are unrestricted or unbound, right? And also variables that are negative within a given boundary, right? So how do we treat unrestricted variables? So when we have unrestricted variables, right, it means that either all of the decision variables or some of them are said to be unrestricted. And if they are unrestricted, if they can take on negative as well as positive values, right? Either negative or positive values. Now, unrestricted variables needs to be converted to positive variables, right? By using, so we have Sj being the unrestricted variable. Then we have to then treat it by using the Sj cap minus X cap, right? So we use this to treat an unrestricted variable. So the Xj, right? The Sj is actually the unrestricted variable, and therefore Sj cap and X cap, they are all greater than or equal to 0. Okay, so this is the best way, the first way to treat unrestricted variable. So we'll solve one of them using this particular example. So assuming that we are maximizing Z and our, let me get my pen here. Okay, so we are maximizing Z is 9x1 plus 18x2, right? So 6x1 plus 3x2 is greater than or equal to 18. 2x1 plus 2x2 is less than or equal to 16. And we know that x1 is actually a rate, maybe a rate of production in a plant. So we say that x1 is actually unrestricted. It can be positive or negative variable, and x2 satisfies the condition, the non-negativity condition, right? So what we do here is that x1 and x2 may be production rate of product 1 and 2, right? So in order to convert, so we have to substitute x1 with x1 cap minus S cap, right? S1 cap minus S cap. So then what we do is that we have to say that MZ is equal to 9 into brackets X, 9 into brackets X1 cap minus S cap, right? Plus 18x2, okay? And we'll say that this is still subject to what are the constraints? 6x1. So we replace 6x1 with x1 cap. So 6x1 cap minus S cap, right? Plus 3x2 greater than or equal to 18. 2x1 cap minus S cap plus 2x2 less than or equal to 16. So then in doing this, then we'll say that x1 cap, x cap, x2, now they are greater than or equal to 0, right? They are greater than or equal to 0. So to expand this, we can just say we are maximizing Z is 9x cap 1 minus 9s cap plus 18 x2, and this is subject to 6 s cap 1, 6 s cap plus 3x2 greater than or equal to 18, 2x1 cap, 2s cap plus 2x2 is less than or equal to 16. So x1 cap, s cap, x2 greater than or equal to 0. All right, so from here, we can actually convert this mixed constraints, the greater than or equal to inequality and the less than or equal to inequality, into a standard form and solve for x1 cap, solve for x cap, solve for x2, and then later on we can replace our x1 is equal to x1 cap minus x cap. We can replace these values and that becomes our x1, right? That's how it works. Okay, so assuming we should walk through this solution, right? We're going to have the following. So this is what we just did in the previous slide. So the standard simplex form can then be translated into that. So we can see the x1 cap, x cap, right, and the 18 x2, and the slack variables that are contributing nothing to the objective function, and also the artificial variable which is negative. That is coming from our first equation, the second, and the third, which is actually the non-negativity rule. So the problem could be solved using the simplex problem now, right? And this is our initial tableau. When we solve, we have this as our pivot number. We do our next iteration. So this is our second iteration here, right? So in our previous lecture, if you want to know how the iterations are done, you'll find them in my previous lecture. So they're just trying to solve them, right? And demonstrate how the final solution can be derived from the simplex. So from here, we can see that there is no positive largest value in the Cj minus Zj, and therefore the solution is optimal from here. So what we do is that we'll say that x2 is equal to 10, x cap is equal to 2, and so x2 is equal to 10, x cap is equal to 2, and x1 is non-basic. x1 cap is actually non-basic. It's not in the solution, so it is actually 0. That's what it means, right? It's not in the solution base, so it's actually 0. And the z is actually 162. So what we do is that we replace our x1 is x1 cap minus s cap, right? And if x1 cap is 0 and s cap is 2, then it means that x1 is actually negative 2 units, right? Which is here. So what this means is that this negative 2 was actually part of the decision variable, but to be able to solve using the simplex, we have to treat it, and that was why we use the x1 cap minus s cap, right? So if you check, you see that yes, it satisfies this. So 6 times 2 is actually negative 12 plus 30, which is actually 18, right? And 18 is actually equal to 18, and therefore is correct. And when I look at this, negative 4 plus 20, which actually 16, and 16 is also satisfying the less than equal to constraint, right? And when you put it in the objective function, it's 9, 18 is negative 18 plus 180, right? And that's giving us 162. which is the Z. So this indicates that this is correct, right? All right, so the second case is when the variables can have a negative boundary, right? So variables can also be negative but bounded, right? So we can have a bounded negative boundary. Like for instance, x1 is greater than or equal to negative 20. This one means that x1 can actually be 0, can be 1, can be 2. Well, these are all positive, right? But since it's greater than negative 20, it means negative 20, negative 19 satisfies this, right? Negative 18 satisfies this. However, x1, right, is then not, satisfying the x1 greater than or equal to 0. So how do we treat this? How do we treat this? So this is handled similar to the unrestricted case, except that it is replaced by the boundary value 20, right? So that means that instead of x1 is equal to x1 cap minus x, in this case, x1 will be equal to x1 cap minus the 20, which is actually the value. So we pick the 20 and not with the negative value, right? Not with the negative value. We can also have negative right-hand side values. Like for instance, we have negative 5x1 plus 2x2 is less than or equal to negative 25, right? So you see that at the initial solution, when x1 is equal to 0 and x2 is also equal to 0, right? Then you're going to have negative 5x1, x2, 25, negative that, and if we are to bring the slack variable, it's equal to negative 25. So then S1, the slack variable, is actually equal to 25. This one again indicates that the slack variable is negative 25, meaning that it doesn't exist, or we have overutilized the resources, right? So how do we then also handle this? All right, so here, what we'll do is that since it will violate the non-negativity constraint, right? So we'll try to resolve this by multiplying through by -1 from the constraint. So it means that we multiply through by -1 so that we turn the equation, the inequality sign, right? So by doing this, we're going to have 5x1 minus x2 is greater than or equal to 25, right? And if you are to work this out, then you can add our various slack variables and also the artificial variables here to solve it using the simplex, right? Okay, now there are other complications. What are they? So complications and their resolution. The first one to look at is a tie for the pivot column. So we said with the pivot column, you should also look at the entering non-basic variable, right, by selecting the largest positive Cj minus Zj, right, for maximization, and Zj minus Cj for the minimization problem, right? So how do you then break a tie? By arbitrarily selecting between the tied values, Yeah, there is no wrong choice. However, the selection of one variable may result in more simplest iterations than the other, right? So there has been several studies to be able to identify which should be the best way or the best one to select, right? but I won't go deep into that. But we want to say that it's very possible there may be a tie in the pivot column. However, you select them randomly. One of them will lead to a longer solution path and the other will not. Yeah, but it will all arrive at the same final tableau. All right, then what happens when we have a tie in the pivot column? For instance, we solve and we get a tableau in this form, right? We solve a tableau in this form. Here you will see that the BIs, which is the BIs, the entering non-basic variable, is actually 40 divided by 4 for the x2 to enter into solution to replace either s1, s2, or s3, right? It's going to replace one of these. So when you divide 40 divided by 4, you get 10. You divide 10 divided by 1, you also get 10. So you see that these two rows, S1 and S3, they tied up for the living basic variable, right? If S3 is chosen arbitrarily, the following tableau will be seen. So this is a tableau that will be seen, right? So it is seen in the second tableau that a basic variable S1 has assumed a value of 0, right? What's the meaning of this? This is an occurrence that results from tied rows and is referred to as degeneracy, right? So when you have tied rows, the other non-selected basic variable, right? The BI of the non-selected basic variable actually, results in a 0 value and is referred to as degeneracy, right? Degeneracy. So the 0 BI value can lead to a series of solutions with the same ZJ value. In this case, it is 60, right? In this case, it is 60. All right. So sometimes when that happens, you will see that we will be looping and getting the same values consistently, right? And we'll refer to it as cycling or looping, right? And can theoretically continue infinitely with the simplex method, never yielding an optimal solution. So in practice, however, after a number of such loops, the simplest procedure will usually proceed normally and reach an optimal solution. So in general, the best way to break the tie between rows is to simply select one arbitrarily, right? So you select one arbitrarily. Tie-breaking methods have also been developed to prevent infinite looping, but this will not be discussed here. So you select one arbitrarily. When you solve and you keep getting multiple solutions and there is cycling or looping, then you must go back and reselect the other value so that after a couple of tableaux, you get the final solution. So that's what it means, right? For you to prevent cycling or looping, there have been some studies done, but we will not look at that. That is tie breaking at this stage or at this level, right? But yes, that is important to know that when you get, when we obtain ties, which are, we have tie in the pivot row, right? We have tie in the pivot row. It generates into degeneracy. That is the BI of the other non-selected basic variable will become 0. And if it attains a value of 0, there is a likelihood that there may be cycling or looping in the next iterations, which will be difficult to yield a particular optimal solution, so it will keep it will continue infinitely, right? So when that happens, you stop the iteration, go back to the other basic variable that was left unselected, select it, and use that as your next iteration, the next tableau, and that should lead to the next final solution, right? When you have done a couple of iterations. All right, if you are into it, you can do more research on how to break ties, and I think it will be interesting to see how you can break the ties so that your tableau will be straightforward. All right, now there is the possibility of having unbound solution. So we know what unbound solution is, right? So in an unbound problem, the objective function can increase indefinitely without ever reaching the constraint boundary. So we talked about it when we're looking at the graphical solution, the graphical solution in earlier lectures, right? You can refer to the earlier lectures, right, on this. So this is a typical unbound problem. So we have x2, right, entering into the basic solution, going to replace either s1 or x1, right? So for us to select from the non-basic solution, right, we surely have to say a 6 divided by -2, which is the numbers in the pivot column. So this is our pivot column. You know about this, right, already. So we need our pivot row. So this is actually infinite, not even not existing. It's actually infinite. So you divide 2 divided by 1, and it's also infinite, right? Or it doesn't exist. So if that happens, what do? So the infinite here is -3, and this one too is -2, right? However, we are looking for positive values, right? We are looking for positive values, or the least positive value here. So it's actually infinite for us, right? So for the tableau, you can see that the entering non-basic variable x2, right, is difficult to select which one is going to replace, right? So it is impossible to select a pivot row. That means that a living basic variable, since both pivot column values are negative. The tableau does not indicate optimal solution, but the process can also not continue. So what then do we do? So what we'll say is that if x2 enters the solution basis, neither of the basic variables act as a bound or the boundary in this problem. So we'll say that the basic variables increase as x2 increases. So the basic variables, the solution will increase s1. So in this example, is it s1 and s1? Yes. So x1 and s1, they increase as the x2 increases, right? And that means that the z function will increase indefinitely, right? Will increase indefinitely. So in general, if a pivot row cannot be selected for lack of a positive ratio, or if all the contributing values, the aij values in the pivot column are negative or they are zeros, the solution is actually referred to as unbound. They are referred to as unbound. Right. Okay. Then what if we have multiple solutions, right? Multiple solutions. So let's use this example as the final tableau for a maximization problem, right? So this is the final tableau. Now we see that the tableau shows that the solution is optimal. Why? Because Cj minus Zj is less than 0, or there is no positive Cj minus Zj value, right? However, the main decision variable, which is x2, is actually non-basic. It's actually not in the solution basis, right? And the Cj minus Zj value is not positive or negative by 0, right? Remember, the Cj minus Zj is the contribution of the value of the non-basic variable when it goes into the solution. So it's a unit contribution, right? Since it's 0, it means that when it enters into the solution, it will actually not change the z, which here is 40. It will not change the profit, right? It will not change the profits at this stage. So what that means is that if we force to put x2 into the solution basis to replace s2, right, it will not result in a change in the profits, that's the values of the z, but will result in a different solution mix, or result in a different solution mix. So let's see if x2 is selected as an entry non-basic variable. This will be the tableau that will arrive. So the previous one had x1 is equal to 10 and s2 is equal to 4. Now you see that if x1, x2 is forced to replace s1, right? If x2 is forced to replace s2 in the solution basis, it will change the solution mix, where x1 now attains a value of 9 and x2 attains a value of 2, but the z function is still 40. So this is also an optimal solution with the same objective function value as the previous, right? As the previous. What it means is that x1 is equal to 10, x2 is equal to 4, or x1 is equal to 9, and x2 is equal to 2. Both are objective, both will give an objective function value of 40. So the tableau shows that the solution is optimal because there is still no Cj minus Zj value with any positive value here. So what this also means is that if we are to use the graphical method to explain this, right? So these are simply the adjacent corner point solutions, which we saw in the graphical method, right? When the solution falls on the line, we say that all points in between the adjacent corner points are also optimal solution, right? They are also optimal solution. So in general, when the Cj minus Zj in the maximization problem, or the Zj minus Cj in the minimization problem, right? When it indicates an optimal solution and the values of any non-basic variables are 0, multiple optimal solutions actually exist, right? So to find the alternative optimal solution, the non-basic variable with Cj minus Zj or the Zj minus Cj value of 0 should be selected as the entering variable, and the Simplex process can continue. It can continue. All right. Our next complication is to look at infeasible problem. So what if the problem is infeasible? How would the simplex treat it? Right, so we saw in the graphical where none of the boundary constraints are actually defining a solution region, right? So here, if we have an infeasible problem, right, we will say that it will normally occur when the problem has incompatible constraints, right, resulting in no common feasible solution space, just as we saw in the graphical method. That's what infeasible problem is. So the constraints do not define any solution region or any feasible solution space, right? So an infeasible problem may not always be apparent as the problem is formulated or during the simplest process. And we said that usually when the constraints, the system of constraints are missing a particular constraint, or when some of the constraints are not defined well, right? That makes a practical problem actually infeasible problem. All right, so at this point, we'll end this lecture here. And our next lecture will look at the two-phased simplest problem. So in case we don't want to use the big M method, we can also use another method called the two-phase simplest problem. So in our next lecture, we'll look at solving the linear programming problems using two-phase simplex method. So thank you very much for being with me, and we will meet in our next lecture. Bye-bye.